So the problem is that angular velocity is in radians per second. What units are we given? We're given revolutions per second, so what do we need to do? We need to convert revolutions into radians. How do we do that? That's what we did over here. You're going to multiply by 2 pi. Yes? So do it.
I did.
You did, but everybody else didn't. Everybody else do it. This is called review. You're not the only person taking the test.
If I was, I would be guaranteed to get the high score.
Well, there you go. And the low score. And maybe we should average your score. We could curve it. You got that. Good.
We
You're
would
becoming
also
a
have to set
mathematician. This is good.
We would also have to set it towards 100.
So revolution per second, what we're doing here is we're converting this to radians per second, Emerson.
Oh, okay.
So I have to convert revolutions. What's the conversion? It's 2 pi. So you're going to multiply it by 2 pi. Now, I caution you because this is one of the most common mistakes that's made. You have to convert revolutions into radians.
So you don't do anything in seconds then? It's just-
No, because it's already in units. Of course, if I told you that I wanted it in, what's the angular velocity in radians per minute,
You'd have to
now you'd have to change the units there too. Yeah, you would.
So you'd have 3.5.
Your unit analysis would be, okay, I want this in minutes on the bottom, so you'd say, well, how many seconds are there per minute? Well, there are 60 seconds per 1 minute, so you'd have to multiply that way, so your seconds crossed out, you had minutes in the bottom. Mr. Eller used to do this. He was very, very good about doing unit analysis when he was here. He had just a whole section where all people were constantly doing unit analysis. And it's important that you get used to thinking about this because it helps you solve problems.
Turbo teaches it a different way though.
Does he?
He uses like train track method or whatever.
Train track. Oh yeah, same idea. That's what Ellen did.
Yeah.
The train track method is where you just make a grid like this, and you keep putting your units in it, and keep canceling out your units. Put the conversion in it. It's the same exact thing. Apparently, put a train track in it. It's exactly the same thing. How about figuring out linear velocity? If I told you, what if I told you that a wheel of radius 26 inches, that's your standard bicycle tire. Wheel of radius 26 inches. What is that? 26?
Not for bicycles.
No, that's around this way. Well, it's okay. It has a radius of 26 inches. We'll just say it's a very large tire. It's like a big bicycle. So you got a wheel of radius 26 inches. It makes 2.5 revolutions per second.
Wow. You're going fast.
Yes, sir. What is the linear velocity in feet per second? Now you notice this is a lovely unit analysis problem because what have I done? I've given you revolutions rather than radians. And what else have I done to make the problem fun?
You're gonna have to convert it to feet.
Yeah, I put in feet and your radius is in inches. Now it's even more fun if I gave you a miles per hour problem, but I probably wouldn't do that to you. So the question is, how do we convert this?
Inches is 220.
You first of all factor down 26 inches down to feet.
Okay, so I could convert this to feet to begin with. I tend to do things the opposite direction. I normally tend to figure everything out. If this is in inches, I figure the problem out in inches, and then at the end I convert everything to feet. But you can do it from the beginning. It doesn't matter either way. And what's the other thing we have to convert?
Revolution.
Revolutions. Okay, so now let's look at our definition. This is a linear velocity problem. So linear velocity, this is in radians per second, and r is measured in whatever linear distance, either feet, inches, meters, whatever. So if I'm going to do this problem, 2.5 revolutions per second, let's convert that into radians per second first. 2.5 revolutions per second is
5 revolutions per second.
It's
For
got
5 radians.
pi. Don't forget, everybody keeps forgetting the pi. Say, how far around the circle? It's 2. No, it's 2 pi. Don't forget the pi. Okay, so this is the same thing. If I multiply this by 2 pi radians per revolution, my revs are going to cancel out, and I've got 5 pi radians per second. Okay, so now I've got radians per second. That's convenient because what is that? Well, that's my angular velocity, and that's this part of the formula right here. Do you see that? I have just figured out the angular velocity, and when I look at the linear velocity formula, this part is this part here. So radians per second is this part. Now what do I need to multiply by?
Radius.
How big is the radius?
26.
26 inches.
The radius is
or-
26 inches.
2
So-
26.
I'll come down here, I'll say 26 inches times 5 pi radians per second. So that's going to be 130 pi radians per second. Now, unfortunately,
Divide by
inch
12.
radius per second. Exactly. Now, I don't have my calculator because somebody is borrowing it. What is 130 times 3.14?
Can't you take the 12 out before you take the pi out? Or the pi in?
Sure, but he has the calculator, so it's easy to do it.
10.833.
What's that?
10.8333333.
No, I wanted you to multiply.
Yeah.
Oh, multiply.
Thank you.
You
It should
end-
get bigger.
You end up with 34 points.
When you multiply the whole thing out, so we're going to take 130 inch radians per second. We're multiplying that by, oh, I got to multiply the pi in. Yeah, it's messy. I need more room.
Divide by 12.
Right,
multiply pi
radians
in.
per second. And I'm multiplying this by 1 foot over 12 inches. So the inch units cancel and it converts everything to feet. And when you take 130 times 3.14 divided by 12, you get
34.
about 34.
0.03. So yeah.
That's fine. 34, and that unit is going to be in feet per second.
You're going really fast.
That's it's moving along reasonably well on a bicycle. 34 feet per second. It's a little over 20, about 22 miles per hour. About 22 miles per hour. So it's
That's not even a bicycle.
That's a big tire. Yes? So you can do linear velocity and linear distances?
So now what would you have to do to have a bicycle? You'd have to have more than 2 turns per second, wouldn't you? To be going the same speed.
Oh, you mean if you're using a real bicycle tire which has a
Yeah.
radius that's smaller than that? Well, all right. If you have a smaller wheel, does it have to turn faster or slower?
Faster.
Yeah, the angular velocity has to be greater to cover the same distance. So your linear velocity, if it's the same, means that your smaller wheel is going faster. I don't remember what the radius of a bicycle tire is. I thought 26-inch wheel, but I don't remember what that is. If that's the diameter, maybe that's the diameter.
Yeah.
That's all the way around. So the 26-inch wheel, maybe that's the circumference.
26 and 28.
So that would mean the difference between a wheel with a radius of 26 inches versus a regular tire. So you double that and divide by 3. It's about 6 times as big. So your bike tire would be going about 6 times faster as it goes around. So. All right. Now we get into the fun stuff. That's the preliminary stuff. Go ahead and cut it.